Our speaker this week is Dr. Kevin Scannell. He's a professor in the Department of Computer Science at St. Louis University in St. Louis, Missouri. He got his bachelor's degree from MIT and then his PhD in mathematics from UCLA. And since then, he's taught at Rice University and is now at St. Louis University. And at St. Louis University, he teaches courses in general CS as well as NLP and machine learning. But he also has an extensive linguistics work. So he's done a lot of work on different kinds of software localization for Celtic languages, working on the GNU project in Linux, the KDE desktop environment, OpenOffice, LibreOffice, Firefox, Thunderbird, Skype, Facebook, all kinds of open source tools. He's also done work on machine translation, for example, Scottish Gaelic to Irish or Manx to Irish machine translation. He's done work on spelling and grammar checking. He's worked on corpora, particularly the Ancrubadan corpus, which is a collection of Webb's corpora of many different languages. He's worked on tweet maps for indigenous languages, Irish dialect detection, OCR for Gaelic fonts, and an online Irish version of Scrabble, which I thought was really interesting. So all over the place, lots of cool stuff. But today, he's going to be talking about computational models for predicting Celtic initial mutations. So whenever you're ready, go ahead and start, Kevin. Thanks.
All right. Thank you, Andrew, for the great introduction. And thanks for the invitation. I'm going to share my screen. I do have some slides. All right. So I want to talk about mutations, and I think for this audience, I'm going to sort of zoom over this first slide pretty quickly, hoping that everybody's at least familiar with the idea here. So mutations are changes to the beginning of words, usually triggered by some contextual clue. I'm going to talk mostly about Irish today, and the examples I'll give will be Irish, but what I'll describe also works for Gaelic. And I'll explain why it's those two in particular in a little bit. So mutations, Bod shoal is a sailboat, but if I say my sailboat, then it changes to Mawad shoal, etc. These are triggered, for example, by gender. If I have an adjective following a noun, depending on the gender of the noun, I will possibly mutate the adjective. So unfairbacht, but unvan wacht. There are lots and lots of examples of these rules or these changes. In the dative case, for example, depending on your dialect, you'll use one of the two, either Linician or Eclipsis mutations in Irish. And then there's a well-known example in the genitive plural. So this is a marker that indicates that noun, if I say the men's toilet, lechris the bar, says that the noun is in the genitive plural because of the eclipsis mutation. So that is my 30-second tour of the topic of my talk. But what I really want to talk about is I want to talk about computational models. And this is something I've been more or less obsessed with since I started thinking about computational tools for Irish about 20 years ago. And the challenge is to produce a computer program that will accurately predict the correct initial mutation in context. The original motivation for this was to produce tools for language learners. So like myself at the time, I was keen to learn the language and use the language online, but to write with some confidence. One of the things that I wanted was to know that I was using the mutations correctly, because in practice, these really are some of the most common mistakes that learners of the language make, especially in the written language. So this was the original motivation. In more recent years, it's turned out that these tools that I've developed for predicting mutations have been useful as well in statistical language modeling. And the language models I've created for Irish in particular underlie a lot of the other tools that I've worked on. So spelling and grammar checking, and then the translation engines that Andrew mentioned between the Gaelic languages all rest on having good statistical language models. So the question is, why is this a difficult problem? The examples on the previous slide make it look like it's maybe not so complicated. And in fact, in many cases, this is a really easy problem. It's preceded by the first person possessive adjective and a noun, then that noun should get the appropriate mutation. And you can write down rules for a lot of these things. And in many cases, these are trivial to predict. But it's one of these things where the easy things are easy and the hard things are hard. And the hard things are exceptionally hard. So they become most difficult when the mutations actually carry some information in the sentence. And in some cases, you have truly ambiguous cases where the computer will be unable to accurately predict. So here's an example where semantics matters, sort of a well-known example where the third person possessive, either meaning his or her, affects the mutation of the following noun. So I should have glossed these, but this says, Kim gave either his or her blessing to, and I've omitted the rest of the sentence, and the challenge is to guess whether that should be his or her in context. This is actual corpus example, so you can try and make your best guess. There are syntactic challenges, so this is another corpus example. That means either the woman was busy at home or the busy woman was at home. And in the case where the adjective busy directly modifies the noun, that should be mutated, otherwise not. The other challenges involve exactly what does correct mean. You can mean that the correct mutation is the one that appears in the official written standard of Irish, but nobody actually follows that standard 100% of the time, even people who think that they are. And then there are just natural variations in the use of these mutations across dialects. And you can't say that one mutation is correct and another is incorrect if they're perfectly valid in one dialect or another. And then the other, maybe the biggest challenge is that the examples and the rules that you write down in a standard, for example, don't often deal with the kind of noise and insanity of real world texts. And I'm interested in processing things like tweets and social media texts, where you have lots of code switching, people mixing in English words and so on. Unusual, either pre-standard or non-standard spellings. And we want software that deals with all of these robustly. So here's the correct answer for those two I've highlighted in red. So the rest of that sentence was Kim gave his blessing to total nuclear disarmament on the Korean Peninsula, right? So that is the context that you needed to decide that that was probably a masculine mutation. And then the other sentence was that the woman was busy at home. So here's how I formulate this problem formally, I guess is the right way to say it. So in Irish and Scottish and Gaelic as well, I say that there are 5 mutations. So there's the null mutation, monition eclipsis, a prefix T, and a prefix H. So what I'll do is I'll take an input text, I strip the mutations from that input text, and then I want to process each word from left to right. All right. And then the goal is for every word where I've stripped the mutation, I want to predict not just what I think the correct mutation is, but actually a probability distribution over these 5 possibilities. And the reason that I want to predict probability distribution and not guess the right answer is, again, because there is variation, and there will be times where the mutation is carrying information and you cannot correctly predict what the right answer is, and the best you can hope for is a probability estimate. So I impose a couple constraints on the problem to make it harder for myself. So one is that I'm only allowed to use context to the left of the target word in order to make predictions. And the reason for this is that I want to use this for statistical language modeling. And the kind of modeling that I do is modeling from left to right. So predicting the probability of a word given the preceding context. That's the standard setup in NLP. I'll come back and talk about why that's a serious challenge. And then the other challenge is just a practical one that I'm looking at this problem sentence by sentence. So I have, when I train a system to do this, I'm training on corpora of text, mostly crawled from the web, but that are sentence shuffled. So segmented by sentence, and then there's no kind of global context from sentence to sentence. And sometimes that matters because sometimes the key context to decide maybe if something is masculine or feminine is in the preceding sentences. And then you need a way of deciding how well you're doing. And what I do is write down essentially an information theoretic estimate of how good my estimates are, or how good my predictions are, I should say. And I'll show you what that looks like in a second. So why just Irish and Gaelic? The reason is that first step, that I take the input text and I strip the mutations. And this is also how I train these models, is I need to be able to algorithmically recognize this word has an eclipsis mutation and this one has a lenition, and so on and so forth. In Irish, you can do this algorithmically and trivially for four of the five. H is a bit of a pain because in Irish we don't write a hyphen between the H and the rest of the word. So here's an example of two words, one of which is a prefix H, and the other one is just the H is part of the word. That's the cognate for hydrogen. And you might say, well, okay, I could look up in a dictionary and see that hydrogen is actually a dictionary word. But even if you use a dictionary, there are ambiguities. So we have the word ashta and hashta, which are both dictionary headwords. And if I see hashta, I don't know whether that means hatch or whether it's a mutated version of ashta. So my solution for Irish is just treat every H as a, well, I don't want to say a mutation, but I strip the H's and I let the model figure out when to put them back. So if I see hydrogen with that H taken away, the model should learn that that H should be put back. Now, this is not sort of the linguistically disciplined thing to do, and it makes it slightly harder for the model to learn sort of the correct, linguistically correct use of that prefix, but it's essentially the only thing I can do if I want to do this in kind of an unsupervised way on large databases of text. Thank goodness Gaelic uses that hyphen after the H, and it means that I can strip all of the mutations unambiguously in the case of Gaelic. Some people leave the hyphen out occasionally, but don't worry about that too much. The issue with the other four languages is that they have mutation systems, but they're not transparent in the same way. And that means that you would need a separate algorithm for demutating in order to do the things that I'm doing here. Those algorithms for demutating themselves need to be trained using machine learning and so on. So it's a bit of a chicken and an egg. I'm working on Manx Gaelic at the moment and have made some good progress on creating parsers, taggers, demutation tools, and so on. So that's coming down the pipe. I wanted to just give a couple examples in these things in context to really show maybe where some of the difficulties are. And the point that I'm trying to make, really, maybe the takeaway of all of this is that mutations really carry virtually no information in these languages. That is to say that when I set up the problem as I've set it up, that I can train the computer to almost 100% of the time make the correct predictions. So, for example, I have these two sentences and I have stripped all of the mutations from these sentences. Now I know we have a mix of backgrounds. I saw a couple Irish speakers join the call. I don't know if anybody wants to speak up and make an attempt at the first sentence. I will tell you there are a couple mutations at least missing. Does anybody want to speak up bravely and guess what these might be? or put it in the chat if you're shy. All right, well, I'll give it away. So in the first sentence, this verb right here should have an eclipsis mutation. That's just because of this preceding particle. Celt here, flee celt, should be certainly a Linguistic mutation. That's sort of a set phrase in some sense. And then there's one tricky case, and that's this one. So this sentence means it is said that she used to carry guns in probably her car, concealed in a flour sack. All right. So this is a possessive combined with the preposition, and the question is it in his car or in her car, or in its car, I suppose, or even in their car? These would all cause different mutations. It's a pretty strong signal, semantically or contextually, that it's she's carrying them in her car, unless maybe there's something in the preceding sentence that suggests that there was a him somewhere. This is a corpus example, and I'll reveal the correct answer in a second, but it really is her car. The point is that this can be exceptionally challenging for the computer to figure out. Probably what's going on when I train, say, a neural network to do this is it's kind of shallowly recognizing this she a couple words before this and sort of using that as a signal. Statistically, most of the time you would get a her when you have that she. But it's hard with neural networks. It's always hard to kind of diagnose what it's really doing. The second example is more subtle, sort of in some ways maximally difficult. And I won't run through all the examples, but there are a couple really tricky ones. So this erduce here should definitely be eclipsis. That's really easy. I'm having a little trouble seeing, but here we have glee, this word glee. Now that's a dative, and typically you would have a choice between eclipsis and lenition. Again, maybe I'll pause for 10 or 15 seconds to see if anybody wants to guess whether they think that should be eclipsis or lenition in this sentence.
Is lenition more common in Donegal?
So Quidine, yes, that is the correct answer, and he has diagnosed the correct reason as well. So, and this is really subtle for the computer. So Guidor is one of the Gaeltacht towns in Donegal. In that particular dialect spoken in and around Guidor, the Linguistic mutation would be the natural one here. And we don't really know that this was written by somebody from that area. It turns out that it was, and Linguistic is correct. This is subtle and difficult for the computer because eclipsis mutation just statistically is more common in the language as a whole. So it's an easy mistake to make, especially when it's difficult to kind of tease out for human, right? For Quidine, you can look at this and sort of detect that clue. For the computer, it's exceptionally difficult. There are other subtleties as well. Peroshta, which means parish here, is both masculine and feminine, depending on the dialect that you speak. And if you look in the dictionaries, feminine, but in Donegal, more often masculine. And that's what happens here. Gui similarly is much more common as a word meaning wind, where it's feminine. In the context of Guidor, it's a word meaning like an inlet, and in that case, it's masculine. These are all exceptionally difficult and challenging. So, so there are the correct answers. Again, her car, Gui with the lenition. This is a masculine noun, so it gets the prefix T. And again, here, I think I maybe said it backwards. So Perosh, the feminine, it gets the lenition there, and so on. So can we train the computer to do this accurately is the challenge. So let me explain very quickly how I evaluate how well I'm doing. So the information theoretic measure that I talked about is really just what information are the mutations carrying in a sentence. So just to explain, if you're not comfortable with information theory and so on, here's my quick explanation. Imagine that we play the same game that we just played in that previous slide, and we have to guess the mutation as you go from left to right. But now you have to make bets. So I'll give you $1 to bet on each word, and you get to spread your bets across the 5 possibilities. So in a case which is almost very certain, if we Celts should be Celts, you might say, I'm going to put almost all my money on the mission and then just kind of spread the remaining penny across the other 4 possibilities just to be safe. In a case like Peroshta, you look up in the dictionary and you say, well, it's usually masculine, so I'll put most of my money on no mutation. But I know that it's feminine in Donegal sometimes, so we'll put almost a quarter on Lanishan, and then the rest are highly unlikely or impossible, so we spread the rest of the money on those. So this is the game that you play, and this is the game that I'm trying to get the computer to play well. Whatever the correct mutation is in context, you lose an amount of money equal to the negative log base 2 of the bet that you make. And I have the graph here. If you forget your logs, what this is saying basically is that if you put most of your money, like 99 cents, and you're correct, you lose nothing, or virtually nothing. If you bet 50 cents and you're correct, it's sort of break even. It's a dollar loss. If you make a very small bet, and it turns out that was the correct mutation, you lose a whole bundle of money. All right, so what the entropy is just your average loss per bet, okay? And it's a very good measure of how hard it is to predict mutations. My claim that these are low entropy features or that mutations carry almost no information is just to say that I can train a system to make these bets near optimally so that this loss is very close to 0. So here's the formula. If you like the mathematics, I write mu for the mutation of a word and sigma for the stripped word. And somehow I'm going to build a statistical model that predicts the probability of a mutation given the preceding word history. And this entropy measure is just the log2 loss of the model on a set of test sentences. So the formula is this. And this is the thing that I'm trying to optimize. And I will be training a neural network to do this. And this is the essentially the objective function. So this is the first approach, is to use neural networks. I'll draw a picture of the model that I use in a second, but it's based on a standard recurrent neural network, LSTM. And the key thing here is that it's trained only on plain text. So this is, you might call it unsupervised learning. This is the reason that it only works for Irish and Scottish Gaelic, because I need to be able to automatically detect what mutation I have just from plain text. The miracle here is that this works is that I am providing just text to the neural network. It doesn't know anything about parts of speech. It doesn't know that what gender is, or even that there is the concept of gender at all. And the way I formulate it sometimes when I explain this to my students is, if I gave you 1,000 books of Irish and you don't speak Irish at all, and I tell you just that there is this thing where you insert an H as the second letter sometimes, could you take those 1,000 books and study for 100 years and figure out what the rules are for where you put those H's? All right, that's really what the challenge is. And again, you don't speak Irish, and what you're looking at is just symbols on a page that you don't understand. That's the challenge. The features that I use, that I feed into the network, are a combination of the words themselves, but then also very critically, the individual characters within the words are critical for making these predictions correctly. For example, Of course, some mutations only apply to certain initial letters. By providing the individual letters to the model, it allows it to learn those generalizations. Another example, with plural nouns, we unite the following adjective, in Irish at least, when the noun has a slender ending. And again, that's something that a generalization that can be learned if the model knows the letters at the end of the word. And then lots of other morphological phenomena that you can learn generalizations over, like all conditional verbs would be mutated. So for those who like neural networks, I thought I would at least put the picture up. With these things, if you're new to it, the model, the input comes from the bottom, sort of flowing up to the top. So you see these stripped, unmutated words at the bottom on the boat. And what's coming in here, the two arrows coming in, are features related to the word and features related to the individual letters of the word. This row right here is the recurrent neural network, LSTM. It processes the input sentences, input words up to the point that I need to make the prediction, passes that on to just more neural network, a dense layer, and then the softmax is what turns that into the probability predictions. So these are a list of 5 numbers, 5 probabilities that add up to 1, the probabilities of each of the mutations. All right, so I claim that this worked well, and the evaluation is according to this log loss. Now, not too many people are doing kind of 5-fold classification problems with log loss, so it's a little strange to report these numbers, but I'll try and explain. If you just made random guesses, then this log loss for the mutations, right? If you just randomly guessed every time, the log loss would be 2.3. It's a log base 205. If you do a very naive algorithm and I just say 20% of the words in Irish are lenited, right? So I'm always going to bet 20% on lenition and so on for the other mutations, then you would get a log loss of about 0.75. etc. For other kind of baselines. If I just look at individual words and I look at historically in the corpus how often they are mutated, and I just use that label distribution per word, I can do slightly better. A trigram model that just considers the 2 preceding words and doesn't consider letters at all does quite well, closer to 0.1. And then the best neural network that I was able to train using the model on the previous slide was trained using 50 million words, vocabulary of the most frequent 100,000 words, gets a log loss of under 0.07. Now, the claim is this is a small number. So the average bits of information carried by mutations in Irish, at least according to this model, is very close to 0. I have my own time. I have a cute sort of visualization of this. I guess I've got about 10 more minutes. I'll waste a minute. So this is a visualization of the network. These are, I think, 5,000 or so nouns. And what I've done is I've colored the masculine nouns blue and the feminine nouns red. And initially, again, it doesn't know that there are nouns and it doesn't know that there are genders. Because gender is critical for the mutation system, you would hope that for this system to work, it really needs to learn that there are masculine and feminine things and it should be able to distinguish them. So that's what this is illustrating is as we get closer to the end, we should see the blue and the red mostly separate from each other. And then the other kind of fun thing that you notice is even within, say, the blue, you'll see that there are clusters, right? So there's sort of a little cluster, tightly packed cluster here. There's another one back here. Those are, say, feminine nouns that all start with either the same letter or similar letters. So for example, there's a cluster for the nouns that start with a vowel. There's a separate cluster for the nouns that start with L and R, which are not mutatable, and so on. So I did this in part because it was fun and interesting, but also to give some confidence that this thing really is learning what it needs to be learning to make these predictions. All right. So this is useful, I said, for language modeling. So was the main reason why I was interested in these probability predictions. My original motivation, and the one I've thought about for a long time, is can you use this for grammar checking, right? For a learner to, when they make a mistake, to accurately diagnose that mistake. It gives us some estimate of how much information is carried by the mutation system, which I think is interesting. I'll have a follow-up slide on that in a second. And then it's really what I thought was fun to look at was the divergence between the predictions that are made using the official standard and what you actually learn from a corpus of actual usage. So the 50 million words that I trained on is mostly crawled from the web. So it's real people using their language online. And there's some divergence there. So you can estimate the amount of information carried by mutations, but you can also actually figure out which ones carry the most information. So I looked at a subset of 10,000 examples, and of those 10,000, the correct label was assigned a low probabilities. This is where the model failed only 167 times. So if you just are saying yes or no, then it was 98% correct. So just those 167 failures contribute more than 3/4 of the total loss of that 0.07. And what's really interesting is that of those 167 places where the model failed, it was not the model's fault. These were actually grammatical mistakes in the test file. So again, it was crawled, all the data was crawled from the web. So these were people on Twitter who maybe didn't have sort of full command of the language and made some kind of a grammatical mistake. And I was careful to distinguish these from kind of just valid free variations. So these were very clearly mistakes, somebody without a full command of the mutations. I mentioned this kind of artificial constraint of only using context to the left. So 30 of these, I could very easily have made the right prediction had I had context to the right. 23 others were perfectly valid, but just not standard forms. So usually sort of dialect spellings that are frequency-wise much less frequent. So the model would typically predict, in this case, the unmutated form of dumb. But again, this is a perfectly valid spelling. And then, of course, everybody's favorite example of where the mutations carry information of the third person possessives. And indeed, this comes up as almost 1/10 of these problematic cases were just places where the model couldn't accurately detect from context what the correct gender was. 9 dialect differences, just mixing up lenition and eclipsis in the dative. A mishmash of others. But what was interesting to me is that there are a lot of things that were not here. So for example, the indirect versus direct relativizers in Irish are distinguished usually by mutation versus eclipsis. And you're taught as you learn the language that this is an important distinction and that it is really flagged by that mutation. The reality is that you can figure it out. And in fact, the model can figure it out just from the surrounding context. It was interesting in part because that's a syntactic thing, and the model is sort of figuring out something about the syntax in order to make that distinction almost perfectly. All right. All right, I've got about 7 minutes to kind of fly through my second model. So I have 2 completely separate approaches to this problem. And the one I just described is what I would call knowledge light or resource light. It goes in knowing nothing about grammar or linguistics and trained just on plain text. The other approach is to kind of go very much in the other direction. So namely, to take a linguistic approach. So do a deep linguistic analysis of the source text before you try and make any predictions. And here, the key observation is that mutations are often triggered by some kind of head and dependent relationship. So a noun and its dependent adjective, and so on. So this led to an approach using tree banks and parsers in the universal dependencies framework. So this is a framework for very much, I think, on the computational side of the parsing world, the syntax world, to produce tree banks and parsers for many of the world's languages in a common framework, right? So here's what these parses or dependency parses look like. So hopefully some of you are sort of broadly familiar with dependency syntax, but if not, the idea is very simple. So words have dependence, and we have every word essentially is connected to its head, right? So a head would have an arrow pointing to its various dependencies. And what you get as a result is you get a tree, all right? And it's a rooted tree rooted at, in this picture, rooted at the main verb of the sentence, all right? So these labels, so every arrow is labeled with essentially a role. So of course there's the root, but then you have things like a determiner dependent of this nominal. We have a prepositional phrase here, and you'll see that the preposition and this determiner are dependents of the noun in the prepositional phrase, which may sound unusual, but one of the principles of universal dependencies is to have the content words be the heads. So in that prepositional phrase, the noun is the head. So this is an example from the Irish tree bank, which, well, I have citations on the next page, but goes back to Teresa Lynn's PhD work. She finished in 2016. So the good news is that there are tree banks for 5 of the 6 Celtic languages. So I mentioned Teresa's PhD thesis in 2016. There is a very good one for Scottish Gaelic by Colin Batchelor. I worked on a Manx tree bank last year, when I was in Connemara. I was supposed to be working on Irish, but on COVID lockdown, I spent a couple months working on a Manx tree bank. I saw Johannes on the call, so welcome. And he and Fran Tyers are responsible for the Welsh tree bank. And then there is also a Breton tree bank, also Fran Tyers with a collaborator. So Cornish is the one language sort of left out in the cold still. If anybody's interested in Cornish, it would be very interesting to have all 6. And I make the point here that I say considerable effort, so certainly some effort has gone into trying to harmonize the annotation schemes. I think we've done probably better kind of among the Gaelic languages, trying to make sure that things are similar. There are some challenges in making sure that all 6 schemes are the same. But the idea with universal dependencies in part is to allow cross-linguistic comparison and really cross-linguistic parsing and transfer learning between languages, because you have the shared annotation scheme. So how do I turn this into a way of predicting mutations? Well, in Irish, and really in most of the languages in universal dependencies, there are also features attached to every word. So this is what an example from the tree bank looks like. And I won't cover everything here, but still have a couple minutes left. Essentially, so this is a sentence, 1 token per line in the sentence. Those tokens are numbered 1 through 7. This column, we have essentially lemmas for these words, part of speech tags, and then these features. All right, so it's sort of key value pairs with kind of standardized names for the keys, And you see that there's a way of marking something as lenited, tense and a mood for the verb, gender, pronouns, case, gender and number for nouns, and so on and so forth. These are numbers pointing to the head of that word. All right, so the subject of the sentence is the pronoun she here, and the head is the main verb, so that's token 1, of course, and then the head itself points to this ephemeral 0 token, which is the root. So the key here are these features. The features have the information we need in terms of gender, number, and so on, but then we also have these dependencies, which tell us, for example, when a noun has a genitive dependent, all right? Or at least this is information that we can extract with a little bit of work from the dependency parse. So this is the strategy. So I should make clear the Irish tree bank is the work of Teresa Lynn and her collaborators and students. So step 1 is to train a dependency parser using Teresa's tree bank, and then a great tool called UDPipe, which allows you to take the tree bank and use machine learning to train the parser. Given an input sentence, I then parse it using UDPipe, and I get a file that looks like the one I just showed you. And then effectively, you take essentially a rule-based approach. So the various mutation rules, an adjective following a feminine noun, and so on, should get a lenition. These get implemented as constraints on what the valid UD feature values can be, given the dependency relations and given the existing features. The challenge to make this work is that it relies on kind of cascades of making the correct predictions. So for example, you need to correctly predict the case of all of the nouns, and more subtly, which nouns are definite versus indefinite. This turns out to be important in Irish for various mutations. You need to make those predictions correctly first before you can hope to make the correct mutation predictions. So this approach works. It allows the big advantage that allows you to do something better than the neural network, which is make linguistically informed and also explainable predictions. So I can say, if somebody leaves out a mutation, I can say, here's the reason why it needs to be there. All right. And then a sort of a nice feature is that because many of the mutations are shared across, at least across the Gaelic languages, computationally, these constraints can be implemented once for all 3 Gaelic languages. There are disadvantages as well. For example, with this approach, you're giving up on the idea of outputting a probability distribution. It's essentially rule-based. And you're also limited by sort of the accuracy of the original parse, which is extremely challenging to get right. And then also each of these kind of cascades of predictions. You accumulate errors with each prediction that you have to make. But this is the second strategy. I don't have, I'm unable to report comparable evaluation numbers, again, because it doesn't output probabilities. What my plan is essentially to combine these 2 models, right? To try and use both the kind of data-driven, robust neural network model, but adding in features and predictions made in this more linguistically disciplined way to, again, hopefully give better results than the ones I reported for model number 1. But that's work to come. So that's probably a good place for me to stop. Thanks.
All right, thanks, Kevin. So we've got a nice set of questions. So I'll just start by asking them, and I'll turn to Mike for the first question, I think. Actually, I can read this one. This one actually makes sense. So you're talking about the 5 different versions of mutations for Irish, and you included none as one of them. And then you also talked about how you strip the characters from all the different words that undergo these mutations. And the question is, how do you strip none? Does that involve removing any content or making, marking it in any way, or does it just leave it the same as it was?
Leaves it the same as it was. Yep. So everything is essentially getting stripped to a none. Okay. And then then your goal is to put the mutations back, and for the ones that should be none, you just leave it alone.
Okay, great. The next question is also from Mike about Welsh right contexts, but I'll let him ask this one.
Sorry, I just puked out a bunch of questions, so you can filter me rapidly. But you mentioned you were only using left context, and I was trying to think of cases of right context. There's a case in Welsh with I can't remember whether the first, second, third, fourth, fifth. So the example I have there is something like the fifth dog versus the fifth cat. And at least in very sort of hyper-correct Welsh, the word for fifth will mutate, even though it's an adjective that precedes the noun, it will mutate based on the following noun. So I don't remember if there are cases like that in Gaelic.
Yeah, so there are certainly challenges. I can't think of a case parallel to that, and I would know Irish better than Gaelic, but yeah, I can't think of a case like that. But I can give a couple examples. Like in Irish, the difference between so just if I have the stripped word da with an accent, so da, the model will make mistakes because it's not sure whether that is, and again, if this is the first word of a sentence, for example, as that word often is, right? It could mean sort of if in the conditional, so it could be da mach something something, or it could be the word for the number two. I could say 2 days ago.
Right.
And if if it's the first word in the sentence, I have no right context at all. There's no way for the model to get that right. So yeah, so the takeaway is that it's an artificial constraint imposed just for the one particular problem of language modeling. If and when I deploy this for the purpose of grammar checking, there's no reason for me to constrain myself that way. Usually people do batch grammar checking. You type the whole sentence or the whole document, and then you say check, right? So you have all the context you need. So yeah, it's just a question of the application.
Thank you.
All right, our next question is from Andrew Carney. I can read it. So he asked, or Andrew can read it.
Yeah, let me just pop in because I actually have two questions. And I actually want to ask the second question first because it follows up on something you just said. So I was going to ask about how I suspect your second system will work better, but how your system deals with, for example, past tense mutation where there is no leftward context and it is initial.
Yeah, no, it's the same. It's the same. That is the other most common case where the lack of right context makes it essentially impossible. So there's the difference between an imperative and past tense at the beginning of a sentence. It's not a coin flip. I mean, the past is more common than the corpus, but yeah, you cannot get that correct.
Okay, so but I expect your dependency system probably could do it.
Well, yeah. So I did not set the problem up the same way. Yeah. So in the dependency system, I'm essentially thinking of it as having the full sentence. Yeah. So really, probably the right thing to say is just forget about that constraint, right? And if I'm going to fairly compare the two models, right, you get to parse the whole sentence and you have the whole thing. If I want to fairly compare that, then I should say that's the neural network gets the whole sentence as well. In which case, I've experimented with this, and it's able to do things like distinguish imperative from past tense, which again suggests that it's because usually there's something syntactic going on. It's able to figure out based on, is this a subject or is this a an object, et cetera, et cetera.
Andrew, can I ask my original first question now?
Yes, you may.
So this also connects a little bit. It's really a question about what your results were. So I was thinking about cases where you have very sort of rare exceptions. I wouldn't even call them exceptions. They're regularities, but they're sort of weird little quirks. So, for example, the one I was thinking of is the fact that in eclipsis contexts, feminine nouns that begin with S take T, which is normally an indication of lenition. And you've got this really sort of weird condition, right? It has to be a feminine noun, it has to begin with S, and it's in an eclipsis context, but it takes the mutation of lenition. And I sort of wondered, is there enough information in the corpus to be able to deduce those kinds of situations?
Yes, and this is one of the reasons that the character level information is so critical. So by including that, it's able to essentially learn generalizations that look like, preposition, determiner, kind of any old word that starts with S, right? You can learn generalizations across all of those examples, right? And thereby kind of make the correct mutation prediction, even for unseen words. That's one of the kind of cool features about this is it'll be, I saw this even in the test set, a verb that didn't appear anywhere in the 50 million words that ended in what looks like a conditional, first person conditional ending. And the model figures out that needs a lenition, for example. And similarly with these kind of unusual cases of, T before an S and so on.
Great, thank you.
Right. It looks like in the chat we have a comment from Kevin about spoken Scottish Gaelic. If you want to just chime in with that, you may.
Yeah, you might have fun if you teamed up with Will Lamb and his voice recognition, because certainly in Scottish Gaelic, maybe it's Irish Gaelic dialects too, you get lenition, for example, an L and N and R to some extent that isn't written. So famous example, if I get it right, Haye Galepi means he went to his bed. Haye Galepi, he went to her bed, which could be important. Or the imperative and the, let's get it right again, Leusa and Lior is an imperative, you read the book, whereas Leusa and Lior is past tense, you read the book. Anyway, you could have fun with more.
And I should have said from the start, this is 100% written language.
Yeah.
I mean, I don't, yeah.
A couple of interesting examples of where you need real world language. There's a famous one, Budilwanya is a bottle, let's get it right, is a milk bottle. It might have lemonade in it, but it's a bottle designed for milk, whereas Budilbanya is a bottle of milk. It might be a lemonade bottle, but it's got milk in it. And another good one is in Broadford Village Hall, there had a big sign outside it for years until the recent renovations it went away. But it said in English, Broadford Village Hall, and in Gaelic it said Tala na ha lehen. There's two words, one means a ford and it's masculine, and the other is a kiln and it's feminine. So Tala na ha lehen meant Broad Kiln Village Hall, which is a spectacular error, but you wouldn't know that without some real world knowledge.
Yeah, thanks, Phoebe. Yeah, in Irish, famously, people talk about Linya Fiona, glass of wine versus a wine glass. I think that's similar to your milk bottle.
All right. Our next question comes from Becky Shields. She's asking if your model can make predictions about nonce words or just unknown words that it hasn't seen during training.
It can, which was very exciting. And it even learned to leave out the mutations on code switched English words, which is really extremely common on Irish Twitter, to have either interspersed individual words or, I don't know, title of a program or a movie or something. And generally speaking, people just won't bother with Irish mutations, even if they might sort of be correct in context on the English words. It learns to leave those out because generally they are. And then again, for either kind of coinages or nonce words or sort of anything that it wasn't seen in training, generally speaking, is able to get those correct. And again, it comes down to the model incorporating individual letters, so it knows. I've given this example in other talks. A made up feminine looking noun. I usually say schnidog in Irish, which is not a word. It doesn't appear in any corpus that I've seen, but if you write it out, any Irish speaker would say that looks like a feminine noun, and they would say schnidog war and not schnidog more. And the model is able to make the correct predictions.
Very cool. So I had a question about how you could maybe extend, or if you could extend this to other Celtic languages that have the non-transparent mutations. So you mentioned, though, for the Irish case with the H's, you just chopped off the H across the board, even when it wasn't necessarily a mutation. So I'm curious if you could do something similar for, Breton or Cornish or Welsh, where you just chop off initial consonants and just let the neural network try to figure out what to add on. If you have any expectations about how that would work based on how, what your results were for those H mutations with Irish.
Yeah, this is a great question. And I've thought about it. I've been thinking about Manx a lot. And so you can do that. Absolutely. You can do an experiment where you just sort of, with no linguistic sensibility at all, just sort of strip things away. And the difficulty is that the model has to learn some kind of regularity, right? It's learning something linguistic.
Mm-hmm.
And so in a sense, like even with the H's in Irish, the model is not really learning where H's go, where the H mutation goes, right? It precedes a vowel when the word le is before it, right? Or ga, et cetera, et cetera. So there are these rules that it should learn, but it's also learning all of these kind of exceptions as well, because of the words where it's not really a mutation. Mm-hmm. And that's not great. That makes it more challenging for the model. The only reason I think I get away with it in the Irish case is because those words with real initial H's, like hydrogen, are extremely unusual, extremely rare. So yeah, this is the advantage of kind of evaluating things numerically in NLP, right? It drops my performance maybe by 0.0001 or something like that, but it's an absurd thing to do linguistically. My intuition, I haven't tried it, but my intuition is that if you do the experiment you suggested, you'll get some results, but they will not be nearly as good because the model's going to have difficulty learning real linguistic regularities.
Yeah. Okay, cool. Looks like we've got a couple more questions from Mike, if he just wants to take it away, about the extra grammatical information, and then about if the mutation triggers are in dependency relationships with the mutating item. So
let me ask the extra grammatical one. So you talked about the information content of the mutations as being fairly small. I agree. But what I'm wondering is, so there's a phenomenon. This is my personal trauma. My personal trauma is that when I speak Welsh to people, I don't sound Welsh, right? And one of the many ways in which I don't sound Welsh, I think, is that I mutate too well. In other words, I follow the rules, right? And I think for my Welsh friends, they think they're talking to somebody on the BBC, right? I sound fake, right? I'm overstating it, right? And so I guess my question is, isn't that a different kind of information, right? So when you said information, I think you meant grammatical information, but there's a social information that the mutations carry. I'm assuming the same is true in the other languages as well. That is, if your use of the mutations communicates something about your formality, whether you're a native speaker or something like that. And I'm wondering, can you model that? Well, one, do you agree it's true? And two, can you model it?
I agree. Yeah, no, I agree broadly that this is a real phenomenon, right? I mean, in Irish, I think it would be more like terminology choices. I think I sounded strange when I was living in Connemara because I wasn't sort of sprinkling in sort of English words as much as people around me for kind of terms for things. So that is part of the information. So I think, for example, when I listed out sort of here are the things that carry the most information, right? One of them was the dative case, right? So the fact that mutation or that prediction is more difficult for the model is saying what? It's saying that dative mutation carries information about the dialect of the speaker, right? So, I mean, it's a separate question. I'm computing this number, which is in bits, right? So it's really information. But the separate question of attributing that to sort of real world phenomena. And yeah, in that case, you could say, I think you could say very clearly, right, that the information that's really being carried is, if I see a lenition in the dative that says, oh, this is written by a Ulster Irish speaker, right? And probably what you're describing as well in Welsh is if I read a text, again, I'm written language only, but if I read a text written by you that had very formal sort of school book style mutations, that maybe that information is communicating this is a L2 speaker, whatever it is. So yeah, I think that's sort of right on.
Thank you.
All right. I think that was all the questions we have. If anyone has any last minute questions, feel free to ask them now. Otherwise, give a minute to decide if you want to ask a question. But otherwise, let's thank our speaker again for a very interesting talk. Feel free to applaud or ASL applause.